All right. Are we sure this is coming through? Reading back? Okay. Sorry we're running a bit behind today. We are today going to be talking about the chain rule of derivatives and automatic differentiation. You remember last class we talked about computation graphs and a naive way of computing the derivative by taking a step and then approximating that derivative with the slope of the function at that point. But there's a better way, and it allows us to compute all of the gradients for all of the weights of our neural network at the same time. And we do that using a nice trick from calculus called the chain rule of derivatives. I'm using okay, that's better. So, try this again. So, if you remember some common analytic solutions derivatives are the following. So, the function of x is some constant times x. The derivative of that function is a. And the function is e to the x. That's the special function whose derivative is itself. The derivative of constant plus x is 1. And then the derivative or just the derivative of x itself is 1. And then the derivative of 1 over x is negative 1 over x squared. And so we're going to do a couple of examples using this basic toolbox of derivatives. So the chain rule of derivatives is used to keep the derivative when you have a chain of functions, or in math it's sometimes called a composition of functions. And that's indicated by this circle composition operator. All this means is f of g of x, or f parentheses g with parentheses x. So basically what we're doing is we're taking the output of one function and feeding it in as input to the next one. And the chain rule of derivatives tells us how to take the derivative in the case of the situation. So suppose we have this composition of functions represented by this large box that encompasses these two smaller boxes, and it produces this funky geometric shape. And we want to take the derivative of that output with respect to the original input to g, which is speed. The way we do that is simply by taking the derivative of diamond to times d sphere. And intuitively, you can think of that as diamond change with respect to sphere is equal to how the diamond changes in response to the cube times how the cube changes in response. Makes decent sense. And in math, the way that you would write that is dx. It have f of q of x, dx equals df of q, and times q dx. So now let's take a function where g is no longer a function of one variable, but it's a function of many variables. And this would be like if g is in the middle of the neural net. Now it's more complicated than just a single chain, because we have this sum over all possible paths that we can go through to get from the input to the output. And so in this case, we're going to say that Z is f of y equals g of x. And so Z equals f of g of x. Now we have this, because G defined as being a function of Rn means that we now have n possible paths that we can take to go from our input x to our output Z. Does that make sense so far? So the way that we do that is have this summation over j. J indexes the number of possible paths, and we sum over dz dyj times dyj dxi. And that gives us the derivative of z with respect to xi. So basically, you can think of it as, we'll see a diagram. Maybe this diagram will help it make more sense. So we spread out, we're just talking about x1 here. There are 5 different intermediate variables, yi's or yj's that depend on x. And so to find the derivative of z with respect to x1, we will sum over all of these paths. That depend on x1. And if we go back to that original slide, that can be expressed more simply as a dot product, where we're taking the derivative of y with respect to x, the derivative of each of the yi's with respect to x, times the gradient of z with respect to y. You'll notice here, f is a function of Rn, R, which means that we have taking the derivative gives us a gradient. And g, in this case, we're just saying that g is going to be, we're just talking about xi. G is a function from R to Rn. And so that wouldn't be called derivative. Well, yeah, so it would also be represented as a vector because we're taking the derivative of each yi with respect to x. So that becomes a vector. The gradient of z with respect to y becomes a vector. And then this sum is just the dot product of those two vectors. So now we're going to give you guys a chance to practice this. So we're going to take a 3-layer neural network, and using the chain rule of derivatives, we will write out how s changes as x changes. And so for starters, I would recommend drawing a computation graph, and you can define whatever intermediate variables that you want to represent the intermediate outputs of these different functions. So right now we're starting with drawing a computation graph. All right, raise your hand if you finish your attempted composition graph. Okay, raise your hand if you haven't yet. You need more time. Okay, so let's see how you did. So this is the computation graph for that function. First we have W times X on the innermost parentheses. We take that output, pass it through an activation function at H, which then gets matrix vector multiplied with another weight matrix. Pass that through another activation function, and then again matrix vector product, which another weight matrix. Give us our final score. Now the next, yeah. Yeah. So first of all, these are not folded. They're not folded. And also, B, H, F, G, H are common letters used for functions. They're also in italics. Yeah. Good. Okay. So next up is you then, and notice that we've also labeled a couple of intermediate steps here. Intermediate outputs. We're calling the output of this operation Z2, the output of this operation A2, Z1, A1, and X. So next step is to try to write down using the chain rule the gradient of S with respect to X. All right, anybody need more time? Okay. So let's see what we have here. So the derivative, this is a nice case where we don't have to deal, at least explicitly, with the forking paths problem. So in this case, derivative of S with respect to X is derivative of S with respect to A1 times the derivative of A1 with respect to Z1 times the derivative of Z1 with respect to A2 with respect to Z2 with respect to X. So that's how we break up that long derivative into individual partial derivatives. And we don't know what H and G are, so we can't evaluate this explicitly all the way through. We'll do that practice in a second. But some of these we can plug in where derivative or Z2 is W3X. So the derivative of Z2 with respect to X is, and actually, I'm going to have someone look this up. I believe it is W transpose. Someone look up the derivative of WX with respect It's W transpose. Yeah, and then A2 is H of C2, C1 is W2A2. So the derivative of C1 with respect to A2 would again be W2 transpose. A1 we cannot evaluate the derivative of because we don't know what T is. And then S, again, the derivative with respect to A1 would be W1 transpose. So I've done this term around a couple of times, automatic differentiation. And basically all it is using computer code to automatically calculate all of these derivatives using the chain rule of derivatives on computation tracks. And so that is what we have PyTorch and TensorFlow and all of these deep learning frameworks. For JAX is a more newly popular framework. All right, so now we're going to do a very simple function, but actually evaluating all of the derivatives. So we're going to start with this expression here. It's the function from R3 to 1 to R. And yeah, I recommend labeling this intermediate variable x plus y as q. And so the assignment is to write the chain rule of derivatives of f with respect to x. This should be a pretty quick one. Let's first draw a computation graph. So we're going to take x and y, apply an add operation, give us our intermediate variable q, and then we will apply the multiply operation on q and z to get our output. And we're going to assign input values. So x is -2, y is 5, and z is -4. We're going to use the chain rule of derivatives to compute the derivative of f with respect to x. So we define q as x plus y. And so we will first define all of our partial derivatives. So derivative of q with respect to x is 1. Derivative of q with respect to y is also 1. Does that make sense to everyone? Okay. The f is qz. So as we substituted x plus y for q, it's now this function. Derivative of f with respect to its input q is z, and derivative of f with z is q. That comes from the identity where we have a constant multiplied by the variable we're taking the derivative of. The derivative is just a constant. Now we have our partial derivatives defined. Now we want our derivatives from the output with respect to each of the inputs, x, y, and z. And I think at this point, you should have enough information to figure this out. So you want to take a stab and see if you can compute the actual number that is the derivative of x, y, and z. Take a minute or two to do that, and then we'll see if we get it right. And actually, yeah, take a minute or two to compute these derivatives and discuss with your neighbor and see if you got the same place. I'm not hearing a lot of conversation.
Negative.
All right, who feels pretty confident about having these derivatives worked out? All right, and back. Yeah, what did you get for your derivative with x, y, and z? Z, Q. So we're looking for actual numbers here, evaluated derivatives. So where you actually plug in these numbers. So you said Z, Q. So that would be -4, and x plus y. Q is x plus y, so 3. -4, 3. Let's see. Yep. So derivative of f with respect to z is just q, like we said, and so that comes x plus y, which is 3. Derivative of f with respect to q is z, so that's -4. Then we'll use the chain rule of derivatives to get the derivative of f with respect to y, which is derivative of f with respect to q, we just found is -4, times the derivative of q with respect to y, which is 1. So again, -4. Then same deal for x. Yes, that is correct. -4, -4, and 3. Okay, let's pause there. Any questions on how we use the chain rule of derivatives to find all of these partial derivatives? Yeah. Yep, that's exactly right. So yeah, we're calculating all of the intermediate partial derivatives, and then when we want to quantify the derivative of the output with respect to one of the inputs, we multiply all of those intermediate derivatives. Yep. Okay, so let's add in some activations. So this is just another visualization of what's happening here. One thing I want to point out here is that in order to calculate all of these derivatives, what we had to do first was calculate the values of all of the intermediate variables before going backwards and computing our other partial derivatives. And so what we would call this is, in the neural network case, would be when we calculate all of the forward outputs, that would be called the forward pass. And then when we calculate all of the gradients, one by one, starting with the outputs and working backwards, that would be called the backward pass. And we see that here as well. Forward pass is in green, and then the backward pass is computed afterwards, and it's in red. And this is the idea of back, if you ever heard of back propagation. Yeah, if you remember last class, we did a technique where we only use forward passes through the network, and we pass small perturbations of the input through the network and use that to calculate the gradient. This back propagation method of going forward and backwards is much more efficient, and in most cases, I won't ever say in all cases, but in general practice, this back propagation algorithm of computing your forward activations and then using those to compute all of the backwards derivatives is what. Yes, ma'am. Yeah, absolutely. Yeah. So that was a great question. So Spencer pointed out that we figured out the symbolic derivative once, and then we use the actual, plug in the actual values to that symbolic derivative. And yeah, that is what you do in general. The legwork of training a neural network is not calculating the symbolic derivative most of the time. Most of your functions already have a little annotation with the backward, with the derivative of that function defined, like hard coded. And so, yeah, the legwork is plugging in the numbers and calculating that. Yeah, actually. Yeah, I think in basically all of the examples we will see, we have symbolic derivative. There are functions out there that for which there is no known symbolic derivative, like the bell curve function, but I am not aware of any cases that we will see that. Yeah, question. So we did actually. So you wanted to walk through how back propagation would work with this example. And you said that we did need to know the output of each step in order to compute it. And actually we did. So it's a very small computation graph, but the place in which we used the forward pass came when we wanted to compute df. Wait. But yeah, when we had to compute df dz, we said that df dz is q, and in order to have q, we had to have gone through this forward operation of adding x and y. Does that make sense? It becomes more apparent when you have a much larger computation graph, but that's an example here where we had to go forward to get those forward values before we could know the derivative. Okay, so we're going to do a more complicated example, and hopefully this will solidify it. You recognize this is the sigmoid function, sigmoid activation function, and we've already given you all of the inputs, computation graph, and all of the forward test values. So now we're going to compute the symbolic derivative at each step, and then plug in values to evaluate the actual derivative at that step. This is a reminder of our identities. So we'll start here. So I'm not sure why the creator of the slides put dz as the derivative of the output with respect to the output. That's always 0. You can just start with dz dh or dz dy, which is the previous output. So yeah, dz dy is the derivative of z with respect to y, where z equals h of y, z equals 1 over y. So this operation here, the 1 over x, corresponds to 1 over 1 plus e to the negative stuff. Okay, so what is the derivative of 1 over x with respect to x?
1 over x squared.
Negative 1 over x squared, yes. Okay, so we are going to plug numbers in. Oh, yeah, ignore that for now. So we're going to plug numbers in. So -1 over x squared. X, the input to that function is 1.37. So -1 over x squared is -1 over 1.37 squared. And then one is just easy. So that gives you -0.53. And that is the derivative of f with respect to y. Now we want to find the derivative of y with respect to what they're calling v. And so we're now looking for the derivative of this bottom part with respect to each of the negative stuff. And in this case, that's just a constant plus the previous input. And so the derivative of f with respect to that is 1. And so then the derivative of f with respect to v is going to be the derivative of f with respect to y times the derivative of y with respect to v. So what was the derivative of y with respect to v? Do you remember? It's 1. So the derivative of f with respect to v will be 1, which is the derivative of y with respect to v, times the derivative of f with respect to y, which is -0.5. Yeah. We got that from here. So yeah, the question is, where do we get the derivative of y with respect to v? So we're saying that y equals 1 plus e to the stuff. And v is e to the stuff. So y is 1 plus v. And so the derivative of y with respect to v is 1. Does that make sense? We just defined y and v as intermediate variables in our computation. So we're just saying that v is the output of e to the negative stuff. So y equals v plus 1, then the derivative of y with respect to v. That question? Exactly, yeah. So yeah, just for the recording, that is the same way that in the previous example we defined q as equal to yeah.
So just to understand exactly that, 1 over x.
Yes. Yep. Okay. We'll do another. So now we're saying that I don't think we have enough name for this variable. We'll call it u. We'll say that u is negative stuff, and v is e to the u. Okay. So then, what will the derivative of v with respect to u be? Exactly. Yep. Okay. So then you will take that, and we know what u is. U is -1. So dv du is e to the -1. And then what will, can someone tell me symbolically what df du will be? There will be 3 partial derivatives. Yeah.
Df du is df y.
That is correct. Yeah. Df du will be df dy times dy dv times dv. Get that? And so we already have -0.53 is the multiplication of the first 2 terms times the negative u gives us -0.2. And you can go all the way back through the computation graph and get your derivatives with respect to your inputs. Does it make sense how we needed to have all of the forward outputs in order to do all of the backwards derivatives? Does that make more sense with a larger computation graph? Seeing some maybes. Yeah, so if you remember, we had you had to use u in order to compute each negative u here. We had to have well, in this case, it was just the derivative was just 1, so we didn't need an output there. But then here we had to have we had to have the previous input x in order to compute -1 over x squared, -1 over 1.37. And so yeah, we need all of the forward inputs in order to compute the backwards derivative. Yes. Yeah, question. Yeah, I'm sorry, I don't have this written up there. Yeah, I'm just gonna, my pen isn't working, so I'll just write the mouse. So, it's y. This is b. All right. Now I'm going to skip forward a little bit because there were some things that I added to this lecture that I think will be really helpful for this upcoming lab. I want to make sure that you get access to them before we close class today. Oh, and actually we're already here. Okay. So has anyone here heard of the law of leaky abstractions? A couple of people. It was actually mentioned in your reading a couple of days ago. The law of leaky abstractions is a term coined by Goldsmith about 20 years ago, and says that basically given an abstraction, and basically all software is abstractions. In other words, given a simplifying layer, at some point that simplification will fail. And a great example of that is neural network training. So you will use PyTorch and will do all this amazing automatic differentiation for you. And then at some point, your neural network will take forever to train, or your gradients will go to 0 and you'll have no idea why. Or any number of problems could occur where normally PyTorch, that simplifying layer is very helpful, but in special cases, it can cause real problems. And so I made this guide to understanding PyTorch, and this will be posted on Learning this week, that answers kind of how is PyTorch working under the hood. And so it answers questions like, why do we implement get, item, and link for dataset classes? And the answer has to do with Python magic methods and understanding how they work and how the data loader uses those functions. What does implementing the forward function do and under the hood? What does loss of stop backward array do? How does the PyTorch optimizer work? Anyway, so all of these, I would definitely recommend reading through all of these. In fact, I'll just add this to this week's reading because I think it will make it a lot easier as you are learning to debug your first neural networks in PyTorch. So, yeah, that's it for today.